Hello, this is probably the last video in my, I guess, 3 video series about a looping multiplication circuit. So what I had done was I had decided to build a multiplier using control logic, in particular looping control logic, so that the control logic will dictate shifting and adding in a specific sequence. So to multiply 2 binary numbers, you can do it by simply shifting and adding numbers. To be clear, I am not saying this is how anyone should build a multiplier circuit. It's simply something I wanted to do. In my first video, I showed a kind of a prototype where I was kind of manually running through the steps. In the second video, I showed a running circuit using a clock. This video is showing the multiplication circuit hooked up to my CPU. I'll just do a brief flyover of my CPU here. It's really moving slow for some reason. Okay. I don't know why it's so slow. Okay. This is roughly my CPU minus the board on the left. ROM is, I'm flying over the ROM. To the right is the program counter. I'm heading towards the RAM there. And that is those bunch of rows with purple. Zero cost buffers are there in front, and there's some registers and an ALU over here. Okay, the multiplication circuit is kind of standing on its own. I have some control boards here for my instruction architecture. You know, you can think about it as micro-coded instructions running the 4 steps for doing multiplication. The first step sends what is in my accumulator, my general purpose register, to mult A register. We'll just call mult A, mult B, and SR for shift register. Okay, so I send the accumulator to mult A, the argument, the instruction argument to mult B. Then I enable the multiplication circuit in this third board, and the fourth board simply copies the mult B results back to the accumulator. If it's of help, I'll just show you this is my one and only general purpose register in my entire CPU. I guess I was inspired, if you will, by the Apple II 6502 processor, which was used in many devices back in the day, home computers, video game consoles. Okay, and it had a single accumulator. That was it. That was its register. And I figured if it worked for the 6502, it would work for me. So that's what I did. Okay. So that's why there's an accumulator. So there's 2 arguments to multiply. One is in the accumulator. The other is stored in memory along with the opcode. So the instruction is basically multiply this very specific value, multiply immediate, by what's in the accumulator. Hopefully that's kind of clear. I can just show you really brief. I don't want to bore anyone, but I'll just show you really briefly. Here's my ROM. And somewhere over here, I will point the cursor right here at the switches setting the instruction. So this instruction here, instruction 8, says multiply whatever's in the accumulator by this value here, and that value happens to be 4. And before it, in my ROM, I say load 3 to the accumulator. So the accumulator has 3. I'm going to multiply it by 4. Answer will be 12. and then I just loop over that set of instructions. Okay. That is what the multiplier circuit is going to be doing. So after setting things up by copying them to the registers, like I showed you via these control boards, these are controlled by a series of instruction cycles via the program counter. There's also something else to note here. The multiplication takes rather a long time. I didn't try to make it efficient. And so there's all these delays, and that is because that is what I computed to be the length of time to do a multiply. And I took the most naive, simple solution I could think of, which is to create a clock hold control line. So while doing this particular step of the multiply instruction, I hold the clock. And this board here simply stops holding the clock after a very long delay of, what is that, 30, 60, 90, 120, 150, 160 some. All right, so let's not even talk about efficiency. That would be crazy talk in this very probably inefficient multiplier. So, don't hire me to build your integrated circuits, I guess. Okay, I'll just briefly explain the multiplier. I've explained in other videos. The multiplier is a mini CPU. It has a clock. It has a series of instruction control boards. It has its own instruction counter driven by the clock. It has 3 registers. It has mult A, mult B, and the shift register. Very roughly speaking, what happens, and I can just go through here because I have them labeled on my control boards. I have a reset until it's enabled. So the reset just constantly writes. I have a 3-bit instruction counter, so this thing constantly writes a 7 to the instruction counter. I write a 7, so the very first time I increment it, I'm pointing at instruction counter 0 control circuit here, control board. This control board says when the instruction counter is 0, do that. And this says when the instruction counter is 1, do that, and etc. Okay, so when the instruction counter is 0, again for my little multiplier mini CPU, it says write B to the shift register. Then I write 0 to B because B is going to contain my running total. And then I basically add the B to what's in A, but not always add. What I do is I look to see what the low bit in the shift register is. That's kind of how that works. If it's a 1, I'm going to add. If it's a 0, I don't add. And then by continuously shifting that shift register to the right and shifting A to the left, I will basically shift and add repeatedly. I add when the control bit, which is in the shift register, is 1. I don't add when it's 0. Then I basically update the ALU. I write the ALU back to B, which is my running total. I then shift the shift register to the right, shift A to the left, and this last thing here is a branch instruction. I just go back to step 2, which updates the ALU, and I repeat that series of steps. It's no different than how you do a shift and add multiply on a piece of paper. All right, so right now this is blinking because it just keeps resetting the integrated. The instruction counter. Excuse me. So it keeps resetting that to 7. Once the program gets around to enabling the multiply circuit, you will see it starting to run these various steps. These little displays will go to yellow. So we're just waiting around for that. And there we go. It's starting to run. The B now contains 0. The shift register contains 4. A contains 3. So I'm multiplying 3 by 4. And now I'm basically going through the shift add steps. Eventually what we'll see in B will be the final tally. it makes no effort to figure out when it's done. That's just handled by just delaying long enough so that it will be done. So now the B register contains 12, which is 3 times 4. So it's done. And in fact, we're back to the multiplication circuit being just sitting around waiting for the CPU to re-enable it, which I do. There's an enable line here. This is the enable pin here. So once that's enabled, the clock will start updating the instruction counter. It starts from 7, increments it to 0, and it goes. Another little feature I'll just show really briefly here. I have 2 quote ROM unquotes. One tells it what to reset the multiplier circuit to when it's not enabled. The other tells it what to jump to on the branch instruction. And those are enabled via the control lines from this set of control boards. So I know I didn't go into a ton of detail. I'm certainly willing to answer questions if anyone is crazy enough to want to build this way, although I suspect there's much better ways to do it. Hopefully that was an interesting video. Thanks for watching.